Hi U10, this is the second slide in the sequence of this week, so this is the second of two, so please make sure you've done the one on current and charge first. There's a worksheet that follows this, and again, if you're watching it as a narrated PowerPoint, find a way of pausing it, or if you're watching it as a video on YouTube, please use the pause button so that you can stop, have a go at those questions. If you get stuck, please come to me via email. It's in the show my homework area, and ask any questions you need. Okay, so we start this lesson off looking at why are we learning all this about electricity. Well, electricity is one of our most commonplace energy transfers in the home or at work, etc. So we want to just remember that there are many different energy stores. So if I give you a little hint, I'm going to get you started. So kinetic energy is an energy store. And if you pause the video and see if you can come up now, it's not named the 8. It's name 8 of the energy stores. There are actually many energy stores. There are considered 7 main ones, but we at GCSE we deal with 8 in particular. So have a crack at those and pause video and see how many you come up with. Okay, so if you're back with me, so kinetic I'll start you off with, which usually reminds people back from P1, where we looked at gravitational potential energy. I should have just written GPE, I know. Okay, in P6 we did nuclear. Hopefully some of you have got this in your clothes, elastic or tension, energy stores. The batteries in your phones, chemical. And what have we got to? So okay, so we would often talk about light and sound, and I've missed one. Oh, of course, the last one, thermal. There you go. So there's a good start. If you don't have those on your revision sheet, there's a chance to throw some information in. So why do we move energy between stores? Well, because we wanted to do work. So that term doing work literally just means transferring energy between stores. So work, moving energy between stores. Nice and simple way of explaining it, and we'll go on from there. Okay, so the objective of this lesson is we're now moving on. We are looking at voltage. We're going to explain this term, potential difference, which is what voltage is. They're two terms that mean the same thing. And we're going to look at it just between 2 points at this stage. We're going to introduce one of my favorite equations, which I use quite regularly when I'm doing any work around the house. So if I want to wire in a new appliance, I need to know how much power it uses. P is for power. And in order to do that, I'm going to need to look at what cables I'm using. So if I use a cable that's too small, it'll overheat and it can be dangerous. So again, this is one that our electricians would use fairly regularly. Okay, so just a quick reminder, hopefully you've done the previous slide. If you haven't, stop, please go back and do the other PowerPoint on current and charge. But I'm just going to flick through these and put them up for you. So if you've done that, you should already have those written down on your revision sheet. Okay, so voltage. Voltage is often referred to as potential difference at school and education. In the real world, it's just called voltage. Okay, so the word potential really means the ability just to do something. Not necessarily it will happen. So at the moment, the power sockets on the walls around you in your home have the ability to do work. So they have a potential of 230 volts, but they're not doing anything. But they do have 230 volts, but they're not doing anything. If you stick your finger in, and do not stick your finger in to prove this, then work can happen. Electricity will flow through you into the floor, hurting you and probably short-circuiting your miniature circuit breakers in your fuse box. So let's not try that and take my word for it. There you go, there's my potential, the potential of year 10s and the word revision. Okay, so UK mains voltage, I was just talking about the power sockets in your home, and this is one of those must-learn facts, and I have a sneaky suspicion, yep, it's going to be big. It's big because this is important. 230 volts, it comes up every year or two that they ask a straightforward question, what's the UK mains voltage? And it is 230 volts. So again, at the moment, those plug sockets on the wall have the potential of 230 volts, but they're not doing any work unless there's something actually plugged into them. Okay, so we like using the water analogy for voltage and current and resistance, how they all come together. So voltage, and this is quite important, so a volt of 1 volt would allow 1 amp to flow through a conductor with 1 ohm of resistance. Now, we haven't done resistance yet. If you think resistance is anything that's called resistance, it's resisting flow. So if we had no resistance, it's really easy for electrical current to flow. It's a little bit like walking down the corridor at school. If I lined up all the year 7s on each side of the corridor, you'd still be able to walk through quite easily. But if I made them bounce around a little bit and run backwards and forwards in front of you, they'd be creating you some resistance. They'd be slowing you down. We would say that they had a high resistance. So, how does this all link into what you've learnt before? All of a sudden, we're talking about joules again. Now, joules is any measurement of energy. This is how it all comes together. It doesn't matter if it's 1 joule of kinetic energy, or 1 joule of gravitational potential energy, or 1 joule of electrical energy. A joule is a joule. So, 1 joule of work has been done to allow 1 coulomb, we're talking about charge here, to go across 1 volt. Okay, so 1 joule is a quantity, it's an amount of energy. So we've measured an amount of charge at a particular voltage. So get all these down on your revision sheet, and when we start with the practice questions, you'll be able to put them into use. So 1 volt is equivalent to 1 joule per coulomb. That's just a simplification of the previous one. Okay, so in this slide we're talking about power. Okay, so now power is where most people will understand. If they look at the front of the microwave, they might see 900 watts written. Now, if you see that in the front of you, it's likely that we've had this discussion before, and a watt is a joule per second. So a 900 watt microwave has 900 joules every second. And it's probably a pretty decent microwave. And if we want to find out what power is, we just multiply the current by the voltage. So here's one of that equation I was talking about earlier. Power equals current times voltage. So I'm going to write this out in full for you underneath. So power equals current, remember we use symbol I for current in our equations, times voltage. Now, this is usually the point where someone points out to me that, well, does it matter what kind of voltage it is? And by kind I mean DC or AC, so alternating current or direct current. So batteries that we use in school and doing cells, well, that's direct current. And the voltage in your house is actually alternating current. It goes backwards and forwards. And actually there's ways at A level that we adjust between these two so that we can actually still use this voltage. But that mains voltage that you were given earlier, 230 volts, you can use that in this equation. And the last point that's coming here, if you increase either voltage or current, power will increase. So if I take my lovely 900 watt microwave and I increase the voltage, okay, then I would expect the power, or the voltage to increase, I'd expect the power to have also increased. Now there's a few things going on here, but we'll just keep it nice and simple for the time being. Okay, so again, we're setting this up for, now I'm going to correct this. I always forget to do this. I'm just rearranging these two, just swapping them around. This makes more sense later on. So we've got our three equations. Now this one over here we've already had from our previous lesson. So now we've got two new equations that we're going to add to our equation sheet. So if you haven't already started this equation sheet, get it started, because you can now see that we've started to add in, we left the equation empty, but this lesson we've already discussed. A current is a 1 volt at 1 ohm. We've already got quit. We've now got the equivalent. Here's another way of remembering this. And we've got PIV. Okay, you just need to remember what the equal sign is. And please don't forget that power is measured in watts. Anything energy is measured in joules. Okay, so we've got a worked example here, guys. If you're working the video, have a crack at this and I will walk you through it. I'll pause for about 5 seconds and then come back to it. Okay, so if you're back with me, we're being asked how much power, and we've been told which equation we're using, but you'd straight away see that we've got voltage, we've got a current, so it's in amps, so the only equation we've got available to us is P equals IV. So again, any physics problem, I'm writing down the equation. Don't need to rearrange it because I'm being asked how much power there is. So in this instance, I've got a current of 3.6 amps times a voltage of 5. 315, that equals 18. 18 watts. Nice and straightforward. Well, there you go. To confirm it, it appears. Press the button. Okay, so we've used PIV in the previous slide, so this time we're using A equals QV, or equivalent. And again, straight away I'm seeing 320 joules, so I know it's energy. So I'll put E over the top of that, so I know which letter I'm using in the equation. I've got 64, that should probably be 64C charge, but we know that coulombs in our equations are the letter Q, and this time around they're asking us what is the voltage, what is the potential difference. They're asking what is the voltage, so we're being asked, I get my pen to work, question mark. So first steps first, I'm still going to write out the equation I need, but this time around I'm going to rearrange it next. So if these two are, I don't know whether you can actually see me pointing, if these two are multiplied together, I want to do the opposite of multiplication, which is divide. So I want to get rid of the q, I want to leave the v on its own, so I'm going to divide this side by q. If I divide this side by q, I also have to divide this side by q. These two q's here cancel each other out, which so now I'm left with v on its own. So I'm just going to tidy this up. V equals E over Q. So now all we have to do is substitute in the numbers that we've done up the top. So we have energy of 320 joules and a charge of 64 coulombs, and 320 divided by 64 is, oh, nice round number, 5 volts. Very important, add the units in. Nope, just to confirm, it's appeared on the screen. Okay, so in this one here, I'm going to let you guys have a crack at this one. The answer will appear in about 5 seconds time, so hit pause. It's in standard form. Write your answer down in standard form. I'll give you a hint. It's a very large number. Okay, so if you're back with me, I'm going to put the answer up and walk you through it. So, straight away, we knew we had to do, electron has a charge of 1.6 times 10 to the minus 19 coulombs. How many electrons make up a charge of 1 whole coulomb? Well, so we just do the inverse, so 1 divided by 1.6 times 10 to the minus 19. And if you, this is a problem that you've probably done in maths a few times, where you try and convert two standard forms, and you'll see it's a lovely, nice big number, 6.25 times 10 to the power of 18. That is an awfully large amount of electrons just to make 1 coulomb. Okay, in order to answer the worksheet later, I'm going to have a quick chat about fuses. Okay, so a fuse's purpose is to protect everything else in the circuit. So if you have a toaster or an expensive coffee machine, and we have a large amount of current, for whatever reason, suddenly goes through that plug, before it gets to your coffee machine, your fuse is going to burn out. Now, there's another side to this, obviously. Let's say your coffee, very fancy, the coffee machine's gone faulty. And it's drawing far too much current. You want to stop it, because if it draws way too much power, it's doing too much work, it's going to get hot, hotter and hotter and hotter, and eventually it's going to catch fire. So that fuse is one way of stopping fires occurring in people's homes. Now, fuses come in different sizes, so why would we limit current? Well, that's one of the reasons. We want to stop fire, we don't want devices to be damaged. And they come in typical fuse sizes of, so if you were to start pulling fuses out, don't do this. If you were to start pulling fuses out of some of your appliances at home, you would find in your bigger appliances, like a coffee machine or a kettle, you'll find a 13 amp fuse, so 13 amps of current. In your smaller things, you might find 3s and 5s. Things like a phone charger, etc., might be 1 amp. Now, again, if you've got a device that, let's say you've got a device that draws 2 amps, there's 2 amps going through it. If you put a 1 amp fuse in, it would blow, because it's more than 1 amp. So you straight away, you want to put a 3 amp fuse in. Now, the question is, why wouldn't you just put a 13 amp fuse in everything? Well, because it's possible that this device that is normally drawing 2 amps goes faulty and draws 11 amps. Now, 11 amps isn't going to blow a 13 amp fuse, and 11 amps might be enough to cause a fire. So we want to use a fuse that's just higher than what we've been asked to protect for. So with 2 amps, we want a 3 amp fuse. Okay guys, so that's the end of the PowerPoint. So this is the time to go straight into that worksheet. I've done a quick little video of that as well. I haven't filled it all in for you, but I would like you to have a go at it, and again, follow my narrated version of it. See if there's anything that doesn't make sense to you. It hopefully walks you through it. Try the examples. They're typical household items, so they're quite relevant to you. And if there's any problems, send me an email.